project is a solar absorption chiller. Here we have Juan R.S.T. Sabel, Adrian Gonzalez, Robert Martin, and myself, Mikael Williams. Our advisor is Dr. Andres Tremonti.
The global impact of our project, we are specifically targeting areas of the world where there's a great need. We are specifically Sub-Saharan Africa, Southeast Asia, Central America, the Middle East, where they have a lot of areas where they have no dependable sources of power. A lot of tents are set up specifically by organizations like the Red Cross, World Health Organization, United Nations, UNICEF. They're set up as field hospitals, administration buildings, sleeping quarters, dining halls. This is the type of temporary situation that we feel are currently experiencing a great need in that they are air conditioning their systems using gas generators to power their AC units. These gas generators produce carbon emissions, are dependent on fossil fuels, so there is a huge opportunity for us to be able to improve upon that system while providing a benefit to our society.
Here you can see the fluids, which will be better described further down in this presentation. We'll be using a portable, self-contained, solar-powered chilled water package AC unit, which will be using an absorption chiller, solar water heating, PV panels, and Stirling engine technology. Our objective is to combine existing technologies to a new application, which will use renewable energy as our power source. This will be a net zero system and will be both packaged and mobile.
The conceptual design is to use a solar collector to collect the solar irradiance, pump that hot water into the absorption chiller and back to the solar collector. The absorption chiller would be pumping chilled water out to a chilled water coil with a supply fan and back to the chiller. The supply fan will be powered by a Stirling engine, which is also a thermal property design, not electrical. So the entire system is all thermomechanical, not using electricity.
Okay, and the absorption chiller uses heat as power. By reducing the pressure in the system, we can boil the water at 40 degrees in the evaporator and 100 degrees in the generator. The hot water that we want to supply will be powered or heated up by the solar water heating up to 250 degrees, which will drive the generator. Water refrigerant in the system exchanges heat to produce chilled water. The waste heat, instead of being rejected, we want to reclaim it. And every 13,000 BTUs of heat we can reclaim, we can produce a ton of cooling. In the absorber, the solar water heating provided by the solar evacuated tubes. We need about 3 to 3.5 square meters to produce 1 kilowatt of power. The Stirling engine, like we said, is also driven by heat. It works on temperature, not a flow rate. Ideally, a temperature difference of 100 degrees, but it can operate at a minimum of 70 and a maximum of 160 degrees. If the Stirling engine can't provide enough power, we want to also include PV panels, which can convert the solar energy into electricity and supply the controls and all the pumps.
Here you can see patterns of this system. We have the Roebuck Corporation in Indiana, the Quotient Jitchum Electronics Company, and the Cooking Valley Bank in Ohio. Here you can see other companies and organizations which are using the respective components. Here you have the absorption chiller, the solar thermal heat, and Stirling engine.
In terms of our budget, we are estimating to spend about $5,500 in our prototype. And we are also estimating that we're going to spend 20 hours man hours per week for 29 weeks for a total of 28,700. And that is estimating that engineer hour is 41.31. This is the cost if we want to build the full size system. This is what the cost will be, which is around $70,000. And our timeline, we are planning to spend 29 weeks for the development of this project. We are currently in week 13, where we have most of the literature is already done. We still need to move for what we have for the conceptual design, put it into reality. So that's what we are working on right now, trying to do the final analysis of the system.
Any questions?
like you're powering quite a few different components solely using solar power. Have you guys investigated exactly how much power is necessary and if that's even possible with the panels that you're going to be able to procure?
Specifically, yeah, we've, that was one of our biggest components that we were looking into on how much we were going to require. And it really depends on a couple of items. Number one is how much of a vacuum can we draw on the refrigerant, on the liquid refrigerant system. The lower the greater the vacuum, the lower the temperature we're going to require. We've looked at several different suppliers, starting with the 20-ton system that would be from Train. It's not manufactured by Train. That one has a very low temperature. We use a lithium bromide and a very high vacuum system, so the temperature required is very low. We looked at Rover. Rover manufactures a 5-ton system. That system uses, I think it's ammonia instead of lithium bromide, and their vacuum is a lot less, so the temperature required will be a lot higher, somewhere north of 300 degrees. So part of our design and implementation is to find that balance where what can we build physically as a prototype and what can we, and as opposed to what is the ideal. You know, and the smaller we go, the higher that temperature is going to be. But again, the smaller we go, the less heat that we have to produce. So there is a break-even point in that design.
We did calculations as far as the amount of heat required, because we're using water-fired, which means we supply hot water to it. So we calculated the heat exchange that we need through the generator, which is where we got the 250 degrees. So we found how much water we need to supply that. So the solar tubes is just for that part. We can add to.
So the solar tubes will boil the water?
No.
Okay.
It's just heating it up to about 250 degrees.
The 250.
Yes.
So the water is heated to 250.
Yes.
F.
Yes.
What temperature is water?
What temperature?
What temperature does
No,
water?
that's why we bring the temperature down inside the system.
Okay.
We bring it down under vacuum, so it's gonna boil at.
Yeah. Okay. So it's under vacuum.
Right.
Yeah. But so using the solar panels that you guys are going to procure, you can get water up to 250
Yes.
in that.
Yes. They have micro trough systems which concentrate it and can get up to 400 degrees.
Okay.
But we only need 250, so that's why and this is more efficient than the PV panels.
And you're sure that, so using that supply of water, you can both power your engine and power the chiller?
Yes. We might, that's the thing, the Stirling engines is the hardest part.
Right.
But that doesn't work on just a temperature, works on a temperature difference. So if we can get, supply 250 degrees, but also supply a lower temperature, then we can get that 100-degree difference and work the Stirling engines at the same time.
Okay. One other quick one, I guess. So you guys are gonna fund the $5,000, or where are you gonna get that?
We will if we have to. We're working on funding. We've talked to companies and we have representation. Me and Adrian both work in the field. We have equipment and also materials available.
We've already procured the absorption. Actually, we procured an absorption refrigerator that we're going to use as part of the conversion. I've also acquired from a project where I removed. On a hospital project that I'm doing at work, we removed some chill water coils. So we've already procured the small coil. So you know, as we're progressing, you know, we're trying to do
All
it
I'm
on
saying is just be
a
careful, right? The whole point of this is not for you guys to go bankrupt to get out of here.
Right.
So just be very careful.
Okay. No, but we're very excited. I mean, if we have to put money into the project,
That's fine. No,
That is,
I don't want you
this
guys
is our
spending
baby.
$5,000 on it. That's the difference, right? So I mean, senior design projects should be more design rather than money. Right.
I guess I have a couple of questions.
Sure.
The solar system will be running water at 250
Yes.
Fahrenheit?
Yeah.
And you have a plan for if, per se, you end up creating vapor or gas in that system, and now all of a sudden you have a problem with flow?
Well, we plan on heating it and storing it. We're having a thermal storage tank, so we're gonna heat the water and keep it in a tank to supply to the system. From the calculations we've done, mostly the evacuated tubes don't produce steam. We don't plan on that, but.
And the tank will have to be completely hermetic?
hermetically sealed.
Right.
And you're going to pressure test that to ensure that you can keep that
Yes.
tank hermetically sealed?
Yes.
Yeah, the idea with this system, again, is that it is completely self-sustained. This is not something that they would set up, show up with parts and set up on site. It's something that would show up on the back of a truck, you know, together with the rest of the convoy, hook up the hoses to the tents, and you know, just make sure you're aiming the panel in the right direction.
Okay, are you, and then the second question I have is on the lithium bromide side. Are you actually going to be managing lithium bromide?
Now, lithium bromide itself, we've done research, is corrosive by itself, so there are additives, but it is not necessarily toxic. It's actually used to treat certain human ailments in the medical field. In reality, it's really just a salt more than.
Okay, but where I go with it, and this is a request on my side, get yourself the material safety data sheet on that material. I want that in your report, and if there is some personal protective equipment required, like gloves and gloves and eyeglasses and gowning, I want a picture in your report showing me that you did it that way.
That's
Because at the end of the day, your safety is very important.
absolutely.
That's why we're not going with the ammonia too, because if this is in an area where people might be around it, I know ammonia is very dangerous. We don't want to mess with ammonia. That's what the system currently is that we bought, so we have to try to convert it or, you know, be very careful with it. But our eventual system is not going to use ammonia. It's going to use the lithium bromide, but we don't want it.
Okay, and that's what you got to do. You got to know what the hazards of that material are and make sure you're protected from it.
Absolutely.
Thank you.
You said there were a couple of companies already manufacturing these. So what sets yours off versus the ones that are currently commercially available?
More specifically, no one is manufacturing a finished product, finished portable product as ours. The manufacturers that are currently producing, Train, Carrier, York, Wilbur, all make large absorption chillers. The smallest ones are the Rover, which make a 5-ton. Those are permanent installation. So none of them are portable, none of them are packaged. We are combining that absorption chiller technology, which is very old, and in its design, we're incorporating that with some of the other thermomechanical technologies in order to produce a finished product that can be incorporated in the third world, in a place where we'll be, be able to provide that benefit without requiring electricity or fossil fuels or anything of that sort.
So you're going to put it on a trailer or put wheels on it? Or...
Exactly.
Do you have other questions? No? Okay.
All right.
Thank you.